Hey there. Imagine waking up one morning and discovering that winter never ended. Not just for a season, not just for a year, but for thousands upon thousands of years. Picture massive sheets of ice stretching as far as the eye can see, glaciers carving through mountains like giant frozen bulldozers, and sea levels dropping so dramatically that entire continents emerge from the ocean floor. This isn't science fiction. This actually happened. And today, we're going to uncover the exact moment when Earth began its descent into one of the most dramatic climate catastrophes in planetary history. What I'm about to share with you will completely change how you think about climate and our planet's fragile balance. Because 26,000 years ago, something extraordinary and terrifying began to unfold. The last glacial maximum wasn't just a cold snap. It was a global transformation so profound that it reshaped continents, drove species to extinction, and pushed our early human ancestors to the very brink of survival. And the most incredible part, we now know exactly what triggered it. But before we dive into that pivotal moment, let me paint you a picture of just how extreme this ice age really was. During the last glacial maximum, permanent ice covered 8% of Earth's entire surface and 25% of all land. The average global temperature plummeted by 6 degrees Celsius, which might not sound like much until you realize that's the difference between a world with thriving civilizations and a world where most of North America disappears under ice sheets 2 miles thick. Sea levels dropped by 125 meters. That's taller than a 40-story building. Imagine draining the ocean to that depth and watching massive land bridges emerge, connecting continents that had been separated for millions of years. The Bering Land Bridge appeared, allowing early humans and animals to migrate between Asia and North America. Britain became connected to mainland Europe. The geography we know today simply didn't exist. The atmosphere itself became a hostile, alien environment. Dust levels were 20 to 25 times higher than today, creating a perpetual haze that blocked sunlight and turned the sky into a brownish, apocalyptic nightmare. Storms raged across the planet with unprecedented fury, and most of the world became cold, dry, and utterly inhospitable to life as we know it. But here's what makes this story absolutely fascinating. Scientists have spent decades trying to understand not just what happened during ice ages, but what actually causes them to begin. And the answer involves a cosmic dance between our planet and the sun that's been playing out for billions of years, combined with a series of environmental triggers that can flip our climate system like a switch. The primary driver behind ice ages lies in something called Milankovitch cycles, named after Serbian scientist Milutin Milankovic, who first proposed this theory a century ago. These cycles describe how Earth's position relative to the Sun changes over vast periods of time, affecting how much solar radiation reaches different parts of our planet. Think of it like this. Earth's orbit around the Sun isn't perfectly circular. It's slightly elliptical, and this shape changes over roughly 96,000 years, sometimes bringing us closer to the Sun, sometimes farther away. At the same time, our planet's axis tilts between 21.5 degrees and 24.5 degrees over a 41,000-year cycle. Finally, Earth wobbles on its axis like a spinning top, completing this motion every 23,000 years. These 3 cycles combine to create variations of up to 25% in the amount of solar energy reaching Earth's mid-latitudes. When these cycles align in just the right way, they can trigger a cascade of climate changes that ultimately plunge our planet into an ice age. But here's where it gets really interesting. Recent groundbreaking research has revealed that Milankovitch cycles alone aren't enough to explain how ice ages actually begin. Scientists have discovered that the formation of ice ages requires a much more complex interaction between orbital changes, ocean currents, and atmospheric composition. One of the most puzzling questions that climate scientists faced was this. If orbital changes caused cooler summers in the northern hemisphere, making glaciation possible, How did massive ice sheets manage to form in relatively mild areas like Scandinavia? The North Atlantic Current should have kept those regions too warm for large-scale ice formation. The answer, it turns out, involves a remarkable chain reaction that begins thousands of miles away in the Canadian Arctic. New research using incredibly sophisticated Earth system models has revealed that the formation of marine ice in northern Canada may be the critical first domino that needs to fall before ice sheets can grow in Scandinavia. Ocean gateways in the Canadian Arctic archipelago act as a control valve for North Atlantic climate, determining whether conditions will allow ice sheets to flourish or fail. When orbital cycles reduce summer solar radiation in the northern hemisphere, the Arctic Ocean begins to freeze more extensively. This marine ice formation disrupts normal ocean circulation patterns, particularly affecting the Atlantic meridional overturning circulation, a massive conveyor belt of warm and cold water that regulates climate across the entire North Atlantic region. As this circulation weakens, the warm waters that normally flow northward from the tropics slow down or even stop entirely. Without this warming influence, temperatures across northern Europe and eastern North America begin to plummet. Snow that would normally melt during summer months starts accumulating year after year, gradually building into the massive ice sheets that define glacial periods. This process creates what scientists call a positive feedback loop. As ice sheets expand, they reflect more sunlight back into space instead of absorbing it. This increased reflectivity, known as albedo, causes even more cooling, which allows ice sheets to grow even larger. The system essentially feeds on itself, driving temperatures lower and lower until vast regions of the planet become locked in ice. But the story doesn't end there. As ice sheets grow, they begin to affect global weather patterns in dramatic ways. The massive weight of ice depresses the land beneath it, sometimes by hundreds of meters. Winds are deflected around these towering ice barriers, creating new storm tracks and weather systems. The jet stream, that high-altitude river of air that guides weather patterns, shifts southward, bringing Arctic conditions to regions that were previously temperate. Meanwhile, all that water locked up in ice has to come from somewhere. The oceans begin to shrink, dropping sea levels and exposing vast areas of the continental shelf. These newly exposed lands become corridors for migration, both for animals and early humans seeking new territories as their old habitats become uninhabitable. The atmospheric composition begins to change as well. As temperatures drop and vegetation dies back, less carbon dioxide is absorbed by plants. But paradoxically, CO2 levels actually decrease during ice ages, dropping to around 190 parts per million compared to over 400 parts per million today. This happens because the cold ocean waters can dissolve more CO2, effectively pulling greenhouse gases out of the atmosphere and amplifying the cooling effect. One theory suggests that as glaciers advance, they grind rocks into fine dust. Winds pick up this iron-rich dust and carry it far out to sea, where it acts as a fertilizer for marine algae. These algae bloom massively, consuming enormous amounts of CO2 from the atmosphere through photosynthesis. When they die, they sink to the ocean floor, taking all that carbon with them and locking it away for thousands of years. The transformation isn't gradual or gentle. Ice core records from Greenland and Antarctica reveal that some of the most dramatic climate changes in Earth's history happened with shocking speed. During the Younger Dryas period, a brief return to Ice Age conditions that occurred about 12,900 years ago, temperatures in Greenland plummeted by up to 10 degrees Celsius in just 3 years or less. Imagine experiencing that kind of climate whiplash. 1 year, your region enjoys relatively mild conditions. 3 years later, you're living in an environment so hostile that most plants and animals simply cannot survive. This is the kind of rapid, catastrophic change that our planet is capable of, and it's happened repeatedly throughout geological history. For early humans living through the onset of the last glacial maximum, the changes would have been gradual at first, but increasingly impossible to ignore. Summers would become shorter and cooler each year, Plants that once thrived would begin to struggle and die. Animal herds would migrate to warmer regions or face extinction. Rivers and lakes would freeze solid for longer periods each year. Archaeological evidence suggests that human populations contracted dramatically during glacial periods, retreating to refugia, small pockets of habitable land where they could survive until conditions improved. These populations became isolated from each other, leading to genetic bottlenecks that we can still detect in modern human DNA. The last glacial maximum represents just the most recent example of Earth's capacity for dramatic climate transformation. Our planet has experienced at least 5 major ice ages over the past 4.5 billion years, each triggered by different combinations of factors, but all sharing the same basic pattern of gradual cooling, followed by rapid ice sheet expansion. The earliest ice age occurred over 2 billion years ago and may have been triggered by one of the most dramatic events in Earth's history, the Great Oxygenation Event. As early life forms began producing oxygen through photosynthesis, this oxygen reacted with methane in the atmosphere. Methane is a powerful greenhouse gas, much more effective at trapping heat than carbon dioxide. When oxygen converted atmospheric methane to carbon dioxide and water, the greenhouse effect weakened dramatically, potentially triggering a global freeze that lasted for hundreds of millions of years. This ancient ice age may have been so severe that it created what scientists call a snowball Earth condition, where ice extended all the way to the equator and covered virtually the entire planet. Evidence for these extreme glaciations comes from glacial deposits found in rocks that were located at tropical latitudes when they formed, suggesting that even the warmest parts of Earth were frozen solid. The most extreme example of this phenomenon occurred during the Neoproterozoic era, between 750 and 580 million years ago. During this period, Earth experienced what may have been the most severe ice ages in planetary history. Geological evidence suggests that glacial ice extended all the way to the equator, creating a frozen world so complete that scientists dubbed it Snowball Earth. Picture this. You're standing on what would one day become the equator, the hottest part of our modern planet, but instead of tropical heat, you're surrounded by an endless expanse of ice and snow. The ocean, normally a deep blue, is frozen solid to depths of several kilometers. The only sounds are the crack and groan of shifting ice sheets and the howl of bitter winds across a landscape that looks more like the surface of a frozen moon than Earth. This wasn't just another cold period. This was a climate catastrophe so extreme that it nearly ended life on Earth before complex organisms had a chance to evolve. The ice albedo feedback loop had gone into overdrive, creating a runaway cooling effect that turned our entire planet into a cosmic snowball hurtling through space. But how does a planet recover from such complete glaciation? The answer lies in volcanism. Even during the most severe snowball Earth conditions, volcanoes continue to erupt, slowly pumping carbon dioxide into the atmosphere. With most of Earth's surface covered in ice, there were no plants or weathering processes to remove this CO2. Over millions of years, volcanic emissions accumulated in the atmosphere until greenhouse gas concentrations became high enough to begin melting the global ice sheet. When that melting finally began, it happened with catastrophic speed. The dark ocean and land surfaces revealed by melting ice absorbed solar radiation much more efficiently than the white ice they replaced. This triggered a rapid warming that may have raised global temperatures by as much as 50 degrees Celsius in just a few thousand years, transforming Earth from a frozen wasteland to a sweltering greenhouse almost overnight. These ancient ice ages set the stage for everything that followed. The stress of surviving through snowball Earth conditions may have driven the evolution of more complex life forms, leading to the explosion of biodiversity that occurred shortly after these glaciations ended. In a very real sense, we owe our existence to these ancient climate catastrophes. Fast forward to more recent geological history, and we find that ice ages have become both more frequent and more predictable. The ice age that began approximately 2.6 million years ago, known as the Quaternary glaciation, is actually still ongoing. What we think of as normal climate today is just a brief warm interlude in a much longer cold period. During this ongoing ice age, glacial and interglacial cycles have repeated roughly every 100,000 years, driven primarily by the Milankovitch cycles we discussed earlier. Each glacial period brings its own unique challenges and transformations, but they all share certain characteristic features that reveal the awesome power of ice to reshape our planet. Consider the Laurentide ice sheet, the massive glacier that covered most of Canada and the northern United States during the last glacial maximum. This single ice sheet contained enough water to lower global sea levels by over 60 meters. It was so thick, in some places over 3 kilometers deep, that its weight actually depressed the Earth's crust beneath it. The sheer mass of these ice sheets created their own weather systems. Cold, dense air would flow down from the ice like an invisible waterfall, creating katabatic winds that could reach hurricane-force speeds. These winds picked up dust and debris, creating massive dust storms that deposited layers of sediment thousands of kilometers from their source. As the ice sheets advanced, they acted like colossal bulldozers, scraping up everything in their path. Soil that had taken thousands of years to develop was stripped away in decades. Entire mountain ranges were carved and sculpted by the relentless grinding of ice. The Great Lakes were gouged out by glacial action, creating some of the largest freshwater bodies on Earth. The biological impact was equally dramatic. Forests that had existed for millions of years were obliterated, replaced by tundra and ice-covered wasteland. Many species faced extinction as their habitats disappeared or shifted thousands of kilometers southward. Those that survived were forced to adapt quickly to radically different conditions or undertake epic migrations to find suitable living conditions. For our early human ancestors, the onset of glacial conditions represented both a crisis and an opportunity. Archaeological evidence suggests that modern humans first began their great migration out of Africa during glacial periods, when lowered sea levels created land bridges that connected previously isolated continents. The Bering Land Bridge, exposed when sea levels dropped during the last glacial maximum, became the highway that allowed humans to first reach the Americas. Similarly, the land bridge connecting Britain to continental Europe allowed early humans to spread across northern Europe, following the retreating edges of the ice sheets as conditions gradually improved. But life during glacial periods was harsh beyond our modern imagination. Early humans had to develop sophisticated survival strategies, creating better tools, more effective hunting techniques, and more durable shelters. The pressure to innovate may have accelerated human technological and cultural development, pushing our ancestors to develop the skills that would eventually lead to agriculture and civilization. Ice core records from Greenland and Antarctica provide us with incredibly detailed information about what daily life might have been like during these periods. The ice contains trapped air bubbles that preserve ancient atmospheres, allowing scientists to reconstruct not just temperature and precipitation, but also atmospheric composition, dust levels, and even the frequency of volcanic eruptions. These records reveal that glacial climates were not just cold and stable. They were characterized by extreme variability, with temperatures swinging wildly over very short periods. What scientists call Dansgaard-Oeschger events, rapid warming and cooling cycles that occurred every few thousand years during glacial periods, could change regional temperatures by 10 degrees Celsius, or more in just a few decades. Imagine trying to plan for the future, when the climate could shift so dramatically within a single human lifetime. Regions that were habitable one generation could become uninhabitable the next, forcing constant migration and adaptation. It's no wonder that human populations remained small and scattered during these periods. The transition out of glacial conditions was often just as dramatic as the transition into them. The end of the last glacial maximum was marked by a series of catastrophic events that reshaped the planet almost as dramatically as the Ice Age itself. Massive ice dams that had held back glacial lakes suddenly failed, releasing floods of biblical proportions. The Missoula floods in the Pacific Northwest provide a perfect example of this phenomenon. When an ice dam holding back glacial Lake Missoula in Montana finally burst, it released a volume of water equivalent to Lake Erie and Lake Ontario combined. This flood scoured the landscape of eastern Washington in a matter of days, carving out coulees and creating the distinctive geology of the region we can still see today. Similar outburst floods occurred around the world as ice sheets retreated. The English Channel was carved by catastrophic flooding when an ice dam holding back a massive lake in the North Sea region finally failed. The distinctive landscape of the Canadian Shield, with its thousands of lakes and rocky outcrops, was created by the complex interaction of glacial scouring and post-glacial flooding. Perhaps the most dramatic example of rapid climate change during deglaciation was the Younger Dryas event. Just as the world was warming up and ice sheets were retreating, something caused temperatures to plummet back to near glacial conditions almost overnight. This cooling lasted for over 1,000 years before ending just as abruptly as it began. The leading theory for what caused the Younger Dryas involves the sudden release of massive amounts of fresh water from North American glacial lakes into the North Atlantic Ocean. This influx of cold, fresh water disrupted the Atlantic meridional overturning circulation, the global ocean current system that transports warm tropical water northward and cold polar water southward. When this circulation system shut down, it triggered a cascade of climate effects that plunged much of the northern hemisphere back into Ice Age conditions. Temperatures in Greenland dropped by up to 10 degrees Celsius in less than a decade. European forests that had been recovering from the Ice Age were once again replaced by tundra. Many large mammals that had survived the Ice Age finally went extinct during this period. The Younger Dryas demonstrates just how fragile our climate system really is. Small changes in ocean circulation or atmospheric composition can trigger massive, rapid shifts that affect the entire planet. It's a sobering reminder that the stable climate we've enjoyed for the past 10,000 years is not guaranteed to continue. Today, as we face the challenge of human-caused climate change, understanding the mechanisms that drove past ice ages becomes more important than ever. The same feedback loops and tipping points that caused dramatic cooling in the past could potentially be triggered by our current warming trend, though in reverse. Some scientists worry that global warming could paradoxically trigger rapid cooling by disrupting ocean circulation systems or by causing massive releases of methane from Arctic permafrost. Others suggest that human emissions of greenhouse gases will prevent the next natural ice age from occurring for hundreds of thousands of years. What's certain is that our planet's climate system is far more dynamic and unpredictable than most people realize. The ice ages represent some of the most dramatic examples of natural climate change in Earth's history, demonstrating the awesome power of feedback loops and tipping points to transform our world in ways that seem almost impossible to believe. The story of ice ages is ultimately a story about the delicate balance that makes life on Earth possible. It's about how small changes in solar radiation, atmospheric composition, or ocean circulation can cascade into planet-wide transformations that reshape continents and drive evolution itself. As we continue to push our climate system into uncharted territory, the lessons of past ice ages become more relevant than ever. They remind us that our planet is capable of changes far more dramatic than anything in recorded human history, and that the stable conditions we take for granted are actually quite rare and precious in the long sweep of geological time. The evidence for these dramatic climate shifts doesn't just exist in computer models or theoretical papers. It's written in stone, ice, and sediment across our planet, waiting for scientists to decode its secrets. Deep beneath the ice sheets of Greenland and Antarctica lie the most detailed climate records ever discovered, preserved in layers of ice that stretch back hundreds of thousands of years. Every winter that passed during the Ice Age left its mark. Snow fell, compressed into ice, and trapped tiny bubbles of ancient atmosphere within its crystalline structure. These bubbles contain the actual air that early humans breathed, complete with precise measurements of carbon dioxide, methane, and other greenhouse gases. When scientists drill down through these ice sheets and extract long cylinders of ice, they're literally pulling up frozen time capsules from our planet's past. The story these ice cores tell is both fascinating and terrifying. They reveal that CO2 levels during the last glacial maximum dropped to just 190 parts per million, compared to over 400 parts per million today. That's a reduction of more than 50% in atmospheric carbon dioxide. But the truly shocking discovery is how quickly these changes occurred. In 1976, a groundbreaking study published in the journal Science analysed deep-sea sediment cores and found remarkably regular variations that matched Milankovitch's calculations perfectly. These sediment layers, built up grain by grain over millions of years, contain microscopic fossils of marine organisms that lived during different climate periods. The chemistry of these fossils reveals ocean temperatures, ice volume, and atmospheric conditions with stunning precision. But perhaps the most dramatic evidence comes from studying the rocks themselves. Across the northern United States and Canada, you can see the scars left by advancing ice sheets with your own eyes. The Great Lakes, those massive bodies of fresh water that define the geography of the American Midwest, are actually giant holes gouged out by glacial ice. Lake Superior alone contains enough water to cover all of North and South America with a foot of water, and it exists only because glaciers over 2 miles thick carved it from solid bedrock. The Finger Lakes of New York, the fjords of Norway, the U-shaped valleys of the Alps, all of these iconic landscapes were sculpted by the relentless, grinding power of glacial ice. As these massive ice sheets advanced, they picked up everything in their path, rocks, soil, entire forests, and carried them hundreds of miles before depositing them in massive piles called moraines. Long Island and Cape Cod are actually just enormous piles of rock and sediment pushed into place by advancing ice sheets. When you walk along these coastlines today, you're literally walking on the debris field left behind by one of the most powerful forces our planet has ever unleashed. The biological evidence is equally compelling and far more sobering. Fossil records show that the transition into the last glacial maximum triggered one of the most significant extinction events in recent geological history. The Pleistocene megafauna, giant mammals that had dominated ecosystems for millions of years, began disappearing as ice sheets advanced and habitats transformed. Imagine encountering some of these creatures. Woolly mammoths with tusks over 4 meters long, cave bears larger than modern grizzlies, giant ground sloths the size of small cars, saber-toothed cats with fangs like curved daggers. These weren't just larger versions of modern animals. They were evolutionary masterpieces perfectly adapted to Ice Age conditions. Yet even they couldn't survive the combination of climate change and increasing pressure from human hunters. The Irish elk, with antlers spanning over 3.5 meters, went extinct as forests gave way to open tundra. Giant beavers the size of bears disappeared as their wetland habitats froze solid. The American cheetah, a predator capable of running down pronghorn antelope, vanished as prey species migrated or died out. Each extinction represented the end of an evolutionary lineage that had survived for millions of years, snuffed out by a climate catastrophe that unfolded faster than evolution could adapt. For early humans living through this transformation, the changes would have been impossible to ignore. Archaeological evidence suggests that modern humans had spread across much of Africa, Asia, and Europe by the time the last glacial maximum began. These weren't primitive cave dwellers. They were sophisticated hunter-gatherers with complex tools Art and social structures. The Cro-Magnon people of Europe, for example, created some of the most stunning cave paintings in human history during the height of the Ice Age. The caves at Lascaux and Chauvet contain artistic masterpieces that rival anything produced by modern artists. These paintings depict the animals they hunted: mammoths, bison, horses, and cave lions, providing us with a window into their daily struggle for survival. But creating art was a luxury these people could ill afford. Most of their time and energy had to be devoted to the constant challenge of finding food and staying warm in a world that was becoming increasingly hostile. They developed sophisticated hunting strategies, learning to drive entire herds of animals over cliffs or into carefully constructed traps. They created specialized tools for different environments, from harpoons for fishing through ice to spear throwers that could bring down large game at a distance. Their clothing had to be perfectly adapted to subarctic conditions. Archaeological discoveries of frozen human remains from this period reveal incredibly sophisticated garments made from multiple layers of animal hide, fur, and even woven plant fibers. These weren't crude animal skins thrown over shoulders. They were carefully designed survival systems that allowed humans to thrive in environments that would kill modern people in hours. The social structures of Ice Age humans also had to adapt to the harsh realities of glacial life. Groups had to be large enough to hunt effectively and share resources, but small enough to find sufficient food in the barren landscape. They developed complex migration patterns, following animal herds across vast distances as seasons changed and food sources shifted. Evidence from archaeological sites suggests that these groups maintained contact with each other across hundreds of miles, trading materials like high-quality stone for tool-making, amber for decoration, and even seashells from distant coastlines. This wasn't just commerce. It was a survival strategy that ensured genetic diversity and shared knowledge across human populations. But the most remarkable adaptation was intellectual. Ice Age humans had to develop an incredibly detailed understanding of their environment to survive. They needed to predict weather patterns, track animal migrations, identify edible plants, and remember the locations of seasonal resources across vast territories. This cognitive demand may have been one of the driving forces behind the evolution of modern human intelligence. The transition into full glacial conditions wasn't uniform across the planet. While northern regions were locked in permafrost, other areas experienced very different changes. The tropics became cooler and much drier as the altered atmospheric circulation patterns disrupted normal rainfall. The Sahara Desert, already arid, became even more extreme, forcing human populations to concentrate around the few remaining water sources like the Nile Valley. In contrast, some regions that are deserts today became more habitable during the Ice Age. Lower sea levels exposed vast areas of the continental shelf, creating new lands for exploration and settlement. The Persian Gulf was almost entirely dry land, with the Tigris and Euphrates rivers flowing through what is now the seafloor. Australia was connected to New Guinea, forming a single massive continent called Sahul. These geographical changes created opportunities for human migration that hadn't existed before. The Bering Land Bridge, exposed when sea levels dropped by over 100 meters, became a corridor between Asia and North America. Archaeological evidence suggests that the first humans to reach the Americas crossed this bridge sometime during the last glacial maximum, beginning one of the most remarkable journeys in human history. Picture the scene. Small groups of hunters, following herds of mammoth and other large game, gradually working their way eastward across the wind-swept tundra of Siberia. They had no idea they were approaching a new continent, just following the ancient rhythms of the hunt that had sustained their ancestors for countless generations. When they finally crossed into Alaska, they became the first humans to set foot in the Americas, carrying with them the tools, knowledge, and genetic heritage that would eventually spread to every corner of two vast continents. The journey south from Alaska required navigating between massive ice sheets that covered most of Canada. Recent archaeological discoveries suggest that these early Americans may have travelled along the Pacific coast, using boats to island hop down the shoreline, while the interior remained locked in ice. By the time the ice sheets began to retreat, human populations had spread all the way to the southern tip of South America, a journey of over 15,000 kilometres accomplished in just a few thousand years. Meanwhile, in the Old World, human populations were dealing with very different challenges. Europe was partially covered by ice sheets and glaciers, but much of the continent remained habitable, albeit under extremely harsh conditions. The Scandinavian ice sheet covered most of northern Europe, while the alpine glaciers extended far down into what are now fertile valleys. Between these frozen barriers, humans survived in refugia, isolated pockets of habitable land, where they waited out the worst of the Ice Age. These refugia became cradles of human culture and innovation. Cut off from other populations by ice and harsh weather, each group developed its own unique adaptations and traditions. Some specialized in hunting reindeer across the tundra. Others became experts at fishing in ice-covered rivers and lakes. Still others learned to gather and process the hardy plants that could survive in periglacial environments. The genetic legacy of these Ice Age refugia can still be detected in modern European populations. DNA studies reveal distinct lineages that trace back to different Ice Age survival groups, each carrying the genetic signature of their ancestors' struggle to survive in a frozen world. These patterns tell a story of isolation, survival, and eventual expansion as the ice retreated and populations reconnected. But survival wasn't guaranteed, even for the most adaptable human groups. Climate records show that the Ice Age wasn't a period of stable cold conditions. Instead, it was characterized by dramatic swings between extreme cold and brief, tantalizing warm periods that could lure populations into expanding their range, only to be caught off guard when conditions deteriorated again. The Younger Dryas event provides a perfect example of how quickly conditions could change. Around 12,900 years ago, just as the ice sheets were retreating and forests were beginning to return, something caused temperatures to plummet back to near glacial conditions almost overnight. In Greenland, temperatures dropped by up to 10 degrees Celsius in less than a decade. Across Europe and North America, the brief recovery was reversed, and tundra conditions returned for over 1,000 years. For human populations that had begun to expand and develop new ways of life as conditions improved, the Younger Dryas was a catastrophe. Archaeological evidence shows that many sites were abandoned as people were forced to retreat to more sheltered locations. The stress of this climate reversal may have accelerated the development of agriculture, as hunter-gatherer populations looked for more reliable ways to secure food in an unpredictable world. The cause of the Younger Dryas remains one of the most hotly debated topics in climate science. The leading theory involves the catastrophic drainage of glacial Lake Agassiz, a body of water larger than all the modern Great Lakes combined that existed along the southern edge of the retreating Laurentide ice sheet. When ice dams holding back this massive lake finally failed, they released a volume of fresh water equivalent to all of North America's Great Lakes into the Atlantic and Arctic Oceans. This enormous influx of cold, fresh water disrupted the Atlantic meridional overturning circulation, the global conveyor belt of ocean currents that transports warm tropical water northward and cold polar water southward. When this system shut down, it triggered a cascade of climate effects that plunged much of the Northern Hemisphere back into Ice Age conditions almost instantly. Alternative theories suggest that the Younger Dryas may have been caused by a cosmic impact event, possibly a comet or asteroid that exploded in the atmosphere over North America. This impact would have triggered massive wildfires, filled the atmosphere with dust and debris, and potentially destabilized ice sheets, leading to rapid climate change. While this theory remains controversial, recent discoveries of impact markers in sediment layers from the right time period have kept it alive in scientific discussions. Whatever caused the Younger Dryas, its effects demonstrate just how quickly our planet's climate system can shift between stable states. The transition out of the Younger Dryas was just as dramatic as its beginning. Ice core records show that the warming that ended this cold period happened even faster than the cooling that started it. In some locations, temperatures rose by over 10 degrees Celsius in less than 50 years, transforming tundra into forest in a single human lifetime. This rapid warming marked the true end of the last glacial maximum and the beginning of the Holocene, the current interglacial period that has provided the stable climate conditions necessary for the development of agriculture and civilization. But the lessons of the Younger Dryas remain relevant today, serving as a stark reminder that our climate system is capable of rapid, dramatic changes that can reshape the world in just a few decades. The end of the Ice Age wasn't just about temperature changes. It involved a complete reorganization of Earth's environmental systems. As ice sheets retreated, they left behind dramatically altered landscapes. The weight of ice had depressed the land surface by hundreds of meters in some areas. As the ice melted, this land began to rebound, a process called isostatic rebound that continues today in places like Scandinavia and northern Canada. This rebound created new coastlines, shifted river courses, and formed thousands of new lakes in the depressions left behind by melting ice. The Great Lakes took their current form during this period, as meltwater found new outlets to the sea and water levels stabilized. The distinctive landscape of the Canadian Shield, with its countless lakes and rocky outcrops, was revealed as ice retreated and exposed the ancient bedrock beneath. The returning vegetation followed predictable patterns as temperatures warmed and precipitation patterns changed. Tundra gave way to grasslands, grasslands to forests, each ecosystem advancing northward as conditions became suitable. But this wasn't a simple linear progression. Different plant and animal species migrated at different rates, creating novel ecosystems that had no modern analogues. Some species that had survived the Ice Age in southern refugia were unable to keep pace with the rapidly changing conditions and went extinct during the warming period. Others, particularly large mammals, that had been perfectly adapted to Ice Age conditions, found themselves unable to compete with new species moving in from the south or to adapt to the changing vegetation patterns. The extinction of the Pleistocene megafauna accelerated during this transition period. Woolly mammoths survived on isolated Arctic islands until just 4,000 years ago, long after they had disappeared from the mainland. Giant ground sloths persisted in South America until around 10,000 years ago. The last cave bears died out in Europe as forests replaced the open landscapes they preferred. These extinctions represent one of the most significant losses of biodiversity in recent geological history. The Ice Age world had supported an incredible diversity of large mammals, many of which had no equivalent in today's ecosystems. Their disappearance marked not just the end of individual species, but the collapse of entire ecological networks that had existed for millions of years. For human populations, the end of the Ice Age created both opportunities and challenges. The retreat of ice sheets opened vast new territories for exploration and settlement. Rising sea levels, however, flooded many of the coastal areas where human populations had concentrated during the glacial period. Entire landscapes that had supported human communities for thousands of years disappeared beneath the waves. The Doggerland region, which once connected Britain to continental Europe, was gradually submerged as sea levels rose. Archaeological evidence suggests this area supported substantial human populations during the late glacial period, but their settlements and way of life vanished beneath the North Sea. Similar stories played out around the world, as post-glacial flooding claimed coastal territories from Australia to North America. Yet the overall effect of deglaciation was to expand the habitable area of the planet dramatically. Regions that had been locked under ice for tens of thousands of years became available for colonization by both humans and other species. The reforestation of vast areas provided new resources for human populations, while the creation of new lakes and rivers offered fresh sources of water and food. This expansion of habitable territory may have been one of the key factors that allowed human populations to grow and develop the surplus food production necessary for complex societies. The stable climate of the early Holocene provided the predictable conditions that made agriculture possible, while the diverse landscapes created by deglaciation offered numerous ecological niches for human exploitation. The legacy of the Ice Ages extends far beyond their immediate effects on climate and landscape. The genetic bottlenecks created by glacial periods shaped the evolution of countless species, including our own. The migrations forced by changing climate created the distribution patterns of plants and animals we see today. The landscapes carved by ice and meltwater define the geography of entire continents. Perhaps most importantly, the Ice Ages demonstrate the incredible dynamism of Earth's climate system. The stable conditions we've experienced during recorded human history represent just a tiny fraction of our planet's climatic potential. The mechanisms that drove past ice ages, orbital cycles, feedback loops, ocean circulation changes, all remain active today, reminding us that the climate we take for granted is neither permanent nor guaranteed. Understanding the Ice Ages also provides crucial insights into how our climate system responds to changing atmospheric composition. The relationship between greenhouse gas concentrations and global temperature, so clearly demonstrated in Ice Age cycles, helps scientists predict how ongoing human activities might affect future climate. The speed with which past climate changes occurred serves as a warning that our current trajectory toward higher greenhouse gas concentrations could trigger equally rapid but opposite changes in the coming centuries. As we face the challenge of anthropogenic climate change, the lessons of the Ice Ages become more relevant than ever. They show us a planet capable of far more dramatic transformations than anything in human experience, driven by mechanisms that we're only beginning to understand. They remind us that the thin shell of atmosphere that makes life possible can be disrupted in ways that reshape entire continents and drive species to extinction. The Ice Ages also reveal the remarkable resilience and adaptability of life on Earth. Despite facing conditions that seem impossibly harsh by modern standards, humans not only survived, but developed the cultural and technological innovations that would eventually lead to civilization. Other species found equally creative solutions, evolving new forms and behaviors that allowed them to thrive in frozen worlds. Yet this resilience has its limits. The extinction of the megafauna shows that even the most successful adaptations can fail when change occurs too rapidly or becomes too extreme. As we push our planet's climate system into uncharted territory, we would do well to remember the lessons written in ice and stone by our predecessors who lived through the last great climate catastrophe our planet experienced. The story of the Ice Ages is ultimately a story about the power of small changes to cascade into global transformations. The slight variations in Earth's orbit that triggered glacial cycles seem insignificant compared to their effects, yet they were sufficient to plunge our planet into conditions that challenge the very survival of complex life. Today, as we alter atmospheric composition at a rate far exceeding anything in the geological record, we must consider whether we might be setting in motion changes just as dramatic as those that created the frozen worlds of our past. The evidence for these catastrophic changes isn't just theoretical. It's carved into the very bedrock beneath our feet and preserved in microscopic detail within ancient ice. When scientists drill into the Greenland ice sheet, they're extracting a frozen library that contains the complete atmospheric history of our planet. Each layer tells a story of what the air was like during a specific year, sometimes down to individual seasons. These ice cores reveal something absolutely shocking about how quickly ice ages can begin. While we often think of climate change as a gradual process taking centuries or millennia, the reality is far more terrifying. During some transitions into glacial conditions, Temperatures in the Arctic dropped by 15 degrees Celsius in less than a single decade. That's equivalent to New York City suddenly experiencing the climate of northern Alaska permanently. But here's what makes this even more remarkable. The ice doesn't just preserve temperature records. Trapped within those frozen layers are actual bubbles of ancient atmosphere, tiny time capsules containing the exact air that early humans breathed 26,000 years ago. When scientists analyze these bubbles, they can measure precise concentrations of carbon dioxide, methane, and other gases that determined whether our planet would be habitable or hostile. During the last glacial maximum, atmospheric carbon dioxide levels plummeted to just 190 parts per million. To put that in perspective, that's barely half the concentration we have today. At those levels, plants struggle to photosynthesize efficiently. Entire ecosystems that depend on robust plant growth simply collapse. The world becomes a place where life itself has to fight for every breath. The transformation didn't happen uniformly across the globe. While the northern hemisphere was locking up under massive ice sheets, other regions experienced equally dramatic but different changes. The tropics, normally the most stable climate zones on Earth, became significantly cooler and much drier. Rainfall patterns shifted dramatically as the altered atmospheric circulation disrupted monsoons and seasonal weather systems that had remained consistent for millions of years. The Amazon rainforest, today one of the most biodiverse places on our planet, shrank to isolated pockets of survival, scattered across a landscape that resembled modern-day savanna. The Congo Basin experienced similar devastation. These weren't just local changes. The lungs of our planet were collapsing, reducing the Earth's capacity to process carbon dioxide and regulate its own climate through the natural cycles that had maintained stability for eons. In Africa, the cradle of human evolution, the changes were particularly dramatic. Lake levels dropped precipitously as precipitation patterns shifted. The Sahara Desert, already formidable, expanded far beyond its current boundaries, creating an almost impenetrable barrier that divided human populations and forced our ancestors into small pockets of habitable land around the few remaining water sources. Archaeological evidence from this period tells a story of incredible human resilience and adaptation. Sites like Blombos Cave in South Africa reveal that despite facing the most challenging climate conditions in human history, our ancestors were creating sophisticated tools, jewelry, and art. They weren't just surviving, they were developing the cognitive and cultural innovations that would eventually allow humans to dominate every environment on Earth. But the cost was enormous. Genetic studies of modern human populations reveal clear signatures of bottlenecks that occurred during glacial periods. Our species came perilously close to extinction multiple times, with global human populations possibly dropping to fewer than 10,000 individuals. Every person alive today carries the genetic legacy of those small groups of survivors who managed to endure conditions that would challenge even our modern technology and knowledge. The physical evidence of Ice Age conditions extends far beyond ice cores and archaeological sites. Across the northern continents, you can see the scars left by advancing glaciers with startling clarity. The Finger Lakes of New York State are perfect examples. These long, narrow bodies of water aren't natural lakes in the conventional sense. They're gouges carved into solid bedrock by glacial ice, moving with the force of billions of tons of frozen water. When you stand at the edge of Lake Seneca or Lake Cayuga, you're looking at wounds in the Earth's surface that were created by ice sheets over a mile thick, grinding their way southward at speeds that seem impossibly slow, yet proved unstoppable. The U-shaped valleys they created are so distinctive that geologists can identify former glacial activity just by looking at the landscape's profile. The Great Lakes themselves represent perhaps the most dramatic example of glacial landscape modification anywhere on Earth. Superior, Michigan, Huron, Erie, and Ontario collectively contain 21% of all the fresh water on our planet's surface. They exist only because advancing ice sheets gouged out depressions so deep that they extend below sea level, then filled them with meltwater as conditions eventually warmed. But the ice didn't just carve and scrape. It transported unimaginable quantities of material across vast distances. Rocks that originated in northern Canada can be found scattered across the American Midwest, carried hundreds of miles by glacial action before being deposited when the ice finally retreated. These erratic boulders, some weighing hundreds of tons, sit in landscapes where their composition makes no geological sense, silent witnesses to the incredible power of moving ice. The biological consequences of glacial advance were equally dramatic and far more tragic. The Pleistocene epoch had supported an incredible diversity of large mammals that had evolved over millions of years to thrive in various environments. As ice sheets advanced and habitats transformed, these magnificent creatures faced challenges that proved insurmountable. The woolly rhinoceros, perfectly adapted to cold grasslands, found its habitat disappearing as forests retreated and were replaced by barren tundra or ice. Giant beavers the size of modern bears watched their wetland homes freeze solid, eliminating the aquatic environments they needed to survive. The cave lion, a predator even larger than modern African lions, lost its prey species as herbivore populations crashed under the pressure of changing vegetation and increasing human hunting pressure. Perhaps most tragically, the mammoth populations that had thrived across northern continents for millions of years began their final decline. These weren't just large elephants. They were evolutionary masterpieces, perfectly adapted to Ice Age conditions with their thick fur, small ears to minimize heat loss, and sophisticated social behaviors that allowed them to survive in the harshest environments Earth could offer. Archaeological sites from this period reveal the complex relationship between humans and these magnificent creatures. At locations like Mammoth Hot Springs in South Dakota, scientists have found evidence of systematic mammoth hunting involving entire human communities. These weren't random encounters. Early humans developed sophisticated strategies for bringing down animals that could weigh up to 6 tons using coordinated group tactics, specialized weapons, and detailed knowledge of animal behavior. The extinction of the megafauna wasn't just an ecological tragedy. It represented the collapse of evolutionary lineages that had survived multiple previous ice ages and climate changes. Something about this particular glacial period was different, more challenging, more final. The combination of rapidly changing climate and increasing human pressure created a perfect storm that even the most adaptable species couldn't survive. Recent advances in ancient DNA research have allowed scientists to track the genetic decline of these species with unprecedented precision. Mammoth populations, for example, didn't just gradually decrease. They went through a series of genetic bottlenecks where small, isolated groups became increasingly inbred and vulnerable to disease, environmental stress, and random catastrophic events. The last mammoth population survived on Wrangel Island in the Arctic Ocean until just 4,000 years ago. These final survivors, isolated on an island roughly the size of Delaware, maintained a population of several hundred individuals for thousands of years after their mainland cousins had vanished. Their bones tell a story of genetic degradation, reduced body size, and increasing vulnerability that finally led to complete extinction during what should have been a relatively stable climatic period. Meanwhile, human populations were developing increasingly sophisticated strategies for survival in the harsh glacial environment. The Gravettian culture, which flourished across Europe between 29,000 and 22,000 years ago, created some of the most advanced stone tools ever produced by prehistoric peoples. Their blade technology was so refined that modern experimental archaeologists struggle to replicate their techniques. These weren't desperate survivors scraping by in harsh conditions. They were innovators, pushing the boundaries of what was possible with the materials and knowledge available to them. Sites like Dolní Věstonice in the Czech Republic reveal evidence of complex social organization, sophisticated hunting strategies, and even early experiments with ceramic technology that wouldn't be fully developed for another 15,000 years. The clothing technology developed by Ice Age humans was particularly remarkable. Analysis of textile impressions preserved on clay figurines suggests they were creating complex, multi-layered garments using techniques that wouldn't be surpassed until the development of modern synthetic materials. They understood insulation, moisture management, and durability in ways that allowed them to survive and thrive in conditions that would quickly kill unprotected modern humans. But perhaps most importantly, they were developing the cognitive and social innovations that would eventually lead to the Neolithic Revolution and the birth of agriculture. The pressure of surviving in an unpredictable, resource-scarce environment forced human groups to develop better planning, more sophisticated communication, and increasingly complex social cooperation. The cave paintings at Lascaux and Chauvet weren't just art. They were information storage systems, ways of preserving and transmitting crucial knowledge about animal behavior, seasonal patterns, and successful hunting strategies. These underground galleries served as libraries and schools where essential survival information could be passed from one generation to the next with remarkable fidelity. The symbolic thinking required to create and interpret these images represents a cognitive revolution that may have been directly stimulated by the challenges of Ice Age survival. When your life depends on understanding complex patterns in animal migration, weather systems, and resource availability, the ability to create and manipulate abstract symbols becomes a matter of life and death. As glacial conditions intensified, human populations were forced into increasingly marginal environments. Yet archaeological evidence shows that they didn't just retreat and wait for better conditions. They explored, adapted, and expanded their range even under the most challenging circumstances. The colonization of Australia, which required crossing at least 90 kilometers of open ocean, occurred during glacial conditions when sea levels were at their lowest. The first Americans crossed the Bering Land Bridge during the height of glacial conditions, then managed to navigate between massive ice sheets to reach the interior of the continent. Within just a few thousand years, human populations had spread all the way to the southern tip of South America, adapting to every environment from Arctic tundra to tropical rainforest along the way. This expansion wasn't random or desperate wandering. Recent archaeological discoveries suggest it was a systematic process of exploration and colonization that required sophisticated planning, advanced technology, and remarkable courage. Groups venturing into unknown territories had to carry with them not just the tools and knowledge needed for immediate survival, but the genetic and cultural diversity necessary to establish self-sustaining populations in completely new environments. The social structures that made this expansion possible were themselves products of Ice Age innovation. Extended kinship networks allowed groups to maintain contact across vast distances, sharing information about resources, weather patterns, and potential threats. Trade relationships developed that could span hundreds of kilometers, ensuring access to high-quality materials for toolmaking, even in regions where such resources weren't locally available. These networks also served as genetic highways, preventing the inbreeding and genetic drift that could doom small, isolated populations. DNA analysis of ancient human remains shows clear evidence of gene flow between distant populations, suggesting that Ice Age humans maintained sophisticated social connections despite the enormous challenges of travel and communication in glacial environments. The tools they created for survival in these conditions were marvels of engineering that modern people often underestimate. A Clovis spear point, the signature tool of early American hunters, represents the culmination of thousands of years of technological development. These projectile points were knapped from high-quality stone using techniques so sophisticated that they could penetrate mammoth hide and reach vital organs with deadly efficiency. But tools were just one aspect of their technological mastery. Ice Age humans developed detailed knowledge of astronomy that allowed them to navigate across featureless landscapes using only the positions of stars and seasonal changes in daylight patterns. They understood meteorology well enough to predict weather changes days or weeks in advance. They possessed botanical knowledge that allowed them to identify edible and medicinal plants, even in the sparse vegetation of periglacial environments. Perhaps most remarkably, they developed psychological and social technologies for maintaining group cohesion and individual mental health under conditions of extreme stress and isolation. The art, music, and storytelling traditions that emerged during this period weren't luxuries. They were essential technologies for maintaining the social bonds and individual resilience necessary for group survival in one of the most challenging periods in human history. The transition deeper into glacial conditions wasn't a steady progression. Climate records reveal that the path toward maximum glaciation was marked by numerous false starts, temporary warmings, and sudden reversals that would have made planning and adaptation incredibly difficult. Populations that expanded their range during brief warm periods might find themselves trapped and struggling to survive when conditions deteriorated again with little warning. One of the most dramatic examples of this climate instability occurred around 39,000 years ago, during what's known as the Lachamp geomagnetic excursion. During this period, Earth's magnetic field weakened dramatically and actually reversed polarity for several hundred years. While this didn't directly cause climate change, it allowed much higher levels of cosmic radiation to reach Earth's surface, potentially affecting atmospheric chemistry and climate patterns in ways we're still trying to understand. The increased radiation may have contributed to the extinction of several megafauna species during this period, including the Neanderthals, whose final populations disappeared from their last refugia in southern Europe around this time. Modern humans, with their more advanced tool technology and social organization, managed to survive this crisis, but the genetic bottlenecks evident in our DNA suggest it was a very close call. These repeated climate crises had profound effects on human cultural evolution. Groups that survived developed increasingly sophisticated risk management strategies, including food storage techniques that allowed them to maintain nutrition through extended periods of scarcity. Archaeological sites from this period show evidence of carefully constructed storage pits, sometimes containing thousands of individual food items preserved using techniques that wouldn't be improved upon for millennia. They also developed increasingly complex social insurance systems. Evidence suggests that successful hunting groups regularly shared their kills with less fortunate neighbors, creating reciprocal relationships that provided security against the inevitable failures and disasters that could befall any individual group. These sharing networks may have been the foundation for the more complex economic and political relationships that would characterize later human societies. The spiritual and intellectual innovations of this period were equally important for survival. The development of shamanic traditions, evident in cave art and burial practices, provided psychological frameworks for understanding and coping with an unpredictable and often hostile world. These weren't primitive superstitions, but sophisticated psychological technologies for maintaining individual and group mental health under extreme stress. The astronomical knowledge embedded in some Ice Age artifacts suggests that these populations were developing increasingly sophisticated models of natural cycles and patterns. Sites like Göbekli Tepe, built at the end of the Ice Age, demonstrate astronomical alignments and mathematical relationships that required generations of careful observation and record-keeping to achieve. This accumulation of knowledge represented a crucial adaptation to Ice Age conditions. In a world where small errors in judgment about weather patterns, animal behavior, or resource availability could mean the difference between survival and extinction, having accurate, detailed knowledge about natural systems became a matter of life and death for entire communities. The pressures of glacial survival may also have accelerated the development of language itself. The complex coordination required for Ice Age hunting, the need to transmit detailed environmental knowledge across generations, and the importance of maintaining social bonds across scattered populations all created strong selective pressures for more sophisticated communication abilities. Recent studies of brain development in modern humans suggest that the neural structures that support complex language and abstract thinking may have undergone rapid evolution during the later Pleistocene, possibly as a direct response to the cognitive challenges of Ice Age survival. If true, this means that our capacity for science, art, and complex social organization may be direct legacies of our ancestors' struggle to survive the most challenging climate conditions our species has ever faced. As the last glacial maximum approached its peak around 21,000 years ago, human populations had developed an unprecedented mastery over their environment. They had colonized every habitable continent, developed sophisticated technologies for survival in extreme conditions, and created social and cultural systems that could maintain group cohesion across vast distances and extended periods of hardship. Yet they remained utterly dependent on natural systems that were themselves undergoing dramatic transformation. The delicate balance between human adaptation and environmental change was about to be tested in ways that would determine whether our species would emerge from the Ice Age as a dominant force or join the growing list of creatures that couldn't adapt quickly enough to survive. The evidence preserved in ice cores, sediment layers, and archaeological sites tells us that this period represents one of the most remarkable survival stories in the history of life on Earth. Small groups of humans, equipped with nothing but stone tools, animal skins, and accumulated knowledge, managed to not just survive, but thrive during conditions that challenged the very existence of complex life on our planet. Their success laid the foundation for everything that would follow. The cognitive abilities, social structures, and technological innovations developed during the Ice Age would eventually enable the agricultural revolution, the rise of civilization, and the complex global society we inhabit today. In a very real sense, we are all descendants of Ice Age survivors, carrying within our genes and our cultures the legacy of their remarkable achievement. But their story also serves as a reminder of how quickly conditions can change and how fragile our relationship with the natural world really is. The stable climate that has allowed human civilization to flourish represents just a brief interlude in a much longer story of dramatic environmental change. Understanding how our ancestors survived the last great climate crisis may be essential for navigating the challenges that lie ahead in our rapidly changing modern world. The archaeological record from this period reveals something truly extraordinary about human resilience. At Kostenki, a site in western Russia dating to around 25,000 years ago, researchers have uncovered evidence of sophisticated winter dwellings built from mammoth bones and hides. These weren't temporary shelters. They were engineered structures designed to withstand months of subarctic conditions, complete with internal hearths positioned to maximize heat efficiency and minimize smoke accumulation. But what's most remarkable is that these structures show signs of being inhabited continuously for generations. Families weren't just surviving the Ice Age, they were building permanent communities in some of the harshest environments Earth has ever produced. Carbon dating of hearth remains shows that fires burned continuously in some of these dwellings for decades, suggesting that knowledge of fire maintenance and fuel management had become so sophisticated that groups could maintain warmth even during the most brutal winter conditions. The hunting strategies developed during this period required levels of coordination and planning that seem almost impossible without modern communication technology. At Předmostí in the Czech Republic, archaeologists have discovered the remains of over 1,000 mammoths, all killed and processed at a single site. This wasn't random hunting. It was industrial-scale resource procurement that required dozens of people working together with perfect timing and coordination. Evidence suggests these hunts involved driving entire mammoth herds into carefully prepared kill sites, possibly using controlled fires to direct animal movement across vast distances. The logistics alone are staggering. A single adult mammoth could provide food for a large group for months, but only if the meat could be preserved and stored effectively. Ice Age humans developed sophisticated techniques for smoking, drying, and freezing meat that allowed them to maintain nutrition through the long, resource-scarce winter months. The bone tools found at these sites reveal another level of innovation that speaks to the desperate ingenuity required for Ice Age survival. When high-quality stone for tool-making became scarce due to changing geography and restricted travel, humans learned to work mammoth ivory and bone into implements that were actually superior to stone tools for many applications. Mammoth ivory needles found at Siberian sites are so fine and precisely crafted that they rival modern surgical instruments. These needles weren't luxury items, they were essential technology that allowed Ice Age humans to create the complex, layered clothing systems necessary for survival in subarctic conditions. Analysis of textile impressions preserved in clay suggests they were creating garments with multiple insulation layers, moisture barriers, and even primitive ventilation systems that could regulate body temperature across a wide range of conditions. The social implications of this technological sophistication are profound. Creating such complex tools and clothing required specialized knowledge that had to be learned through years of apprenticeship. This suggests that Ice Age communities had developed educational systems sophisticated enough to transmit complex technical knowledge across generations, even under conditions where a single failed harvest or unsuccessful hunt could mean starvation for the entire group. But perhaps the most telling evidence of human adaptation comes from the genetic record itself. Recent advances in ancient DNA analysis have revealed that human populations during the last glacial maximum weren't just larger than previously thought. They were more genetically diverse, suggesting that different groups had developed distinct adaptations to specific environments and were maintaining contact across surprisingly large distances. Populations in Eastern Europe developed genetic variants that improved their ability to metabolize fat, crucial for survival on the high-fat diet necessary in Arctic conditions. Groups in Central Asia evolved enhanced cold tolerance mechanisms that are still detectable in their modern descendants. These weren't random mutations. They were systematic evolutionary responses to the specific challenges of Ice Age survival. The speed of these genetic adaptations suggests that natural selection was operating with unusual intensity during glacial periods. Traits that provided even small survival advantages spread rapidly through populations, while individuals lacking these adaptations were quickly eliminated from the gene pool. This created a kind of evolutionary pressure cooker that may have accelerated human development in ways we're still trying to understand. Meanwhile, the planet itself was undergoing transformations that would have seemed like science fiction to earlier generations of life. The massive ice sheets covering northern continents weren't static frozen barriers. They were dynamic systems that created their own weather patterns, generated their own winds, and literally reshaped the surface of the Earth through their immense weight and movement. The Laurentide ice sheet, which covered most of Canada and the northern United States, was over 3 kilometers thick in some areas. Its sheer mass was so enormous that it actually deformed the Earth's crust beneath it, pressing the land downward by hundreds of meters. This isostatic depression created a bowl-shaped depression in the continent that affected drainage patterns, created vast lakes, and fundamentally altered the geography of North America. The ice wasn't uniform or stable. Within these massive sheets were rivers of faster-moving ice called ice streams that could flow at rates of several kilometers per year, carrying rock debris and reshaping the landscape with the grinding power of billions of tons of moving frozen water. These ice streams carved the distinctive valleys we see today in places like the Hudson River Valley and the Great Lakes region. But the most dramatic effects occurred at the edges of the ice sheets, where the boundary between frozen and unfrozen land created some of the most extreme and unstable environments Earth has ever produced. The periglacial zones, areas just beyond the ice margins, experienced temperature swings that could range from -40 degrees Celsius in winter to above freezing in summer, creating freeze-thaw cycles that shattered rocks and created the distinctive landscape features we associate with former glacial regions. These periglacial environments were characterized by permafrost extending hundreds of meters deep into the ground, with only a thin, active layer that thawed during brief summer months. The ground was perpetually unstable, heaving and cracking as water expanded and contracted with seasonal temperature changes. Building any kind of permanent structure required intimate knowledge of soil behavior and engineering techniques that wouldn't be formally understood until the development of modern geotechnical science. Yet humans not only survived in these conditions, but developed sophisticated strategies for predicting and managing the environmental instability. Archaeological evidence suggests they understood seasonal patterns of ground movement well enough to position their dwellings in locations that would remain stable throughout the annual freeze-thaw cycle. The biological consequences of these extreme conditions extended far beyond the obvious challenges of cold and resource scarcity. The periglacial environment created unique ecological niches that supported plant and animal communities unlike anything existing today. The mammoth steppe ecosystem that covered much of northern Eurasia and North America was characterized by incredibly high productivity, despite the harsh conditions. This grassland ecosystem supported biomass densities that exceeded even the most productive modern grasslands. Vast herds of mammoth, bison, horse, and reindeer grazed across landscapes that stretched from Spain to Alaska, creating a continuous belt of high-protein food sources that early humans learned to exploit with remarkable efficiency. But this productivity came at a cost. The mammoth steppe ecosystem was inherently unstable, dependent on very specific climate conditions that could shift rapidly as ice sheets advanced or retreated. When conditions changed, the entire ecosystem could collapse within decades, forcing both animals and humans to migrate vast distances in search of suitable habitat. The collapse of the mammoth steppe ecosystem, which began around 15,000 years ago as glacial conditions started to ameliorate, represents one of the most dramatic ecological catastrophes in recent geological history. Within just a few thousand years, an ecosystem that had supported millions of large mammals across entire continents simply disappeared, replaced by forest and tundra environments that could support only a fraction of the previous biomass. This ecological collapse coincided with and may have accelerated the extinction of the Pleistocene megafauna. As their primary habitat disappeared, large mammals found themselves competing for increasingly scarce resources while simultaneously facing mounting pressure from human hunters who had become increasingly skilled and organized. The timing of these extinctions reveals something crucial about the relationship between climate change and species survival. Many of the extinct species had survived multiple previous glacial cycles, suggesting they were well adapted to cold conditions. What made this particular transition different was the combination of climate change and human pressure, creating a perfect storm that even the most successful Ice Age species couldn't survive. Woolly rhinoceros, cave bears, giant deer, and dozens of other species that had thrived for millions of years disappeared within just a few millennia. Their extinction represents not just the loss of individual species, but the collapse of entire evolutionary lineages that had taken millions of years to develop. For the surviving species, including humans, this created both opportunities and challenges. The disappearance of large predators like cave lions and short-faced bears reduced one source of mortality for human populations. But the loss of large herbivores eliminated reliable sources of protein and materials that had sustained Ice Age communities for thousands of years. This resource crisis may have been one of the driving forces behind the development of agriculture. As traditional hunting became less reliable due to megafaunal extinctions, human groups were forced to develop alternative strategies for food procurement. The intensive management of wild plant resources that characterizes the transition to agriculture may have begun as a desperate response to the ecological disruption caused by the end of the Ice Age. But the transition wasn't uniform or immediate. Different human populations responded to these challenges in different ways, leading to the incredible diversity of survival strategies we see in the archaeological record from this period. Some groups doubled down on hunting, developing increasingly sophisticated techniques for pursuing smaller, faster prey. Others turned to marine resources, developing fishing and sea mammal hunting technologies that allowed them to exploit coastal environments. Still others began the systematic cultivation of wild plants, gradually developing the agricultural techniques that would eventually support complex civilizations. These different strategies led to different evolutionary pressures and may have contributed to the physical and genetic diversity we see in modern human populations. The climate instability that characterized the end of the Ice Age created additional challenges that required constant adaptation and innovation. The Younger Dryas event, which plunged much of the Northern Hemisphere back into near glacial conditions for over 1,000 years, caught many populations off guard, just as they were beginning to adapt to post-glacial conditions. Archaeological sites from this period show clear evidence of population crashes and cultural disruption. Many settlements were abandoned as groups retreated to more sheltered locations. Trade networks that had developed during the initial warming were disrupted, forcing communities to become more self-sufficient, just as resources were becoming scarcer. Yet some groups managed to not just survive, but thrive during this climate reversal. The Clovis culture in North America, for example, spread rapidly across the continent during the Younger Dryas, suggesting they had developed technologies and strategies that were particularly well suited to unstable, challenging conditions. The end of the Younger Dryas marked the true beginning of the modern interglacial period and set the stage for the development of agriculture and complex societies. But the lessons learned during the Ice Age continued to influence human development long after conditions stabilized. Many of the cognitive abilities that we consider uniquely human, including abstract thinking, long-term planning, and complex social cooperation, may have been shaped by the selective pressures of Ice Age survival. The ability to maintain group cohesion under extreme stress, to innovate rapidly in response to changing conditions, and to transmit complex knowledge across generations, all became essential for survival during glacial periods. These abilities proved equally valuable as humans began to develop agriculture and build the first cities. The organizational skills required to coordinate mammoth hunts translated directly to managing agricultural communities. The risk assessment abilities developed for surviving in unpredictable periglacial environments became crucial for managing the uncertainties of early farming. The social technologies developed during the Ice Age, including systems for sharing resources, resolving conflicts, and maintaining group identity across large distances, provided the foundation for the more complex political and economic institutions that would characterize later civilizations. Even our modern relationship with technology bears the imprint of Ice Age innovation. The incremental improvement of tools, the systematic testing of new techniques, and the careful preservation and transmission of technical knowledge all reflect approaches to innovation that were literally matters of life and death for our Ice Age ancestors. The artistic and symbolic traditions that emerged during this period also had profound effects on subsequent human development. The cave paintings at Lascaux and Altamira weren't just early art, they were information storage and transmission systems that allowed complex knowledge about animal behavior, seasonal patterns, and hunting strategies to be preserved and shared across generations. These early symbolic systems provided the foundation for the development of writing, mathematics, and the other symbolic technologies that would eventually enable complex civilization. The cognitive abilities required to create and interpret symbolic representations were first developed as survival tools in Ice Age environments. The spiritual and philosophical traditions that emerged during this period also reflect the unique challenges of Ice Age survival. The animistic beliefs evident in Ice Age art and burial practices suggest that these populations had developed sophisticated frameworks for understanding their relationship with the natural world and their place within larger ecological systems. These belief systems weren't primitive superstitions, but practical philosophies for living in close connection with natural processes. They emphasized careful observation of natural patterns, respect for the power of natural forces, and the importance of maintaining balance between human needs and environmental constraints. Many of these principles remain relevant today as we face our own environmental challenges. The Ice Age experience demonstrates that human survival depends on maintaining a sustainable relationship with natural systems, and that disrupting these relationships can have catastrophic consequences for both human societies and the broader ecosystem. The Ice Age also provides crucial insights into the relationship between climate change and social development. The rapid climate transitions that characterized glacial periods created strong selective pressures for social innovation, leading to the development of increasingly sophisticated systems for sharing information, coordinating group activities, and managing resources. These social innovations often proved more important for survival than technological developments. Groups with better communication, more effective leadership, and stronger social cohesion consistently outcompeted those with superior tools but weaker social organization. This pattern suggests that our response to current environmental challenges will depend as much on social and political innovation as on technological solutions. The Ice Age experience demonstrates that human societies are capable of remarkable adaptation when faced with existential challenges, but only if they can maintain the social cooperation and information sharing necessary for coordinated action. The end of the last glacial maximum didn't mark the end of climate instability. Throughout the Holocene, smaller climate fluctuations have continued to challenge human societies and drive cultural change. The medieval warm period, the Little Ice Age, and other climate anomalies have all left their marks on human history, demonstrating that climate variability remains a constant feature of the human experience. Understanding how our Ice Age ancestors adapted to far more dramatic climate changes provides perspective on our current challenges. While anthropogenic climate change represents a new type of environmental disruption, the basic principles of adaptation, resilience, and sustainability that allowed humans to survive the Ice Age remain relevant today. The Ice Age experience also demonstrates the importance of maintaining genetic and cultural diversity as insurance against unpredictable environmental changes. The populations that survived glacial periods were those that had developed diverse strategies for resource procurement, maintained connections with other groups, and preserved knowledge about multiple different environments and conditions. Today, as we face the prospect of rapid environmental change, maintaining this kind of diversity may be crucial for long-term human survival. The homogenization of human cultures and the loss of traditional ecological knowledge represent potential vulnerabilities that could prove dangerous if current environmental trends continue. Perhaps most importantly, the Ice Age reminds us that human survival has always depended on our ability to work together, share resources, and maintain social cooperation, even under the most challenging conditions. The individualistic ethos that characterizes much of modern society would have been a death sentence for Ice Age populations. The challenges we face today, from climate change to resource depletion to biodiversity loss, require the same kind of coordinated, long-term thinking that allowed our ancestors to survive the Ice Age. The technologies may be different, but the fundamental requirements for survival remain the same. Careful observation of natural systems, sustainable resource use, social cooperation, and the wisdom to adapt quickly when conditions change. The legacy of Ice Age survival lives on in every human alive today. We carry in our genes, our cultures, and our ways of thinking the accumulated wisdom of thousands of generations who learned to thrive in one of the most challenging periods in Earth's history. That legacy represents both a testament to human adaptability and a guide for facing the environmental challenges that lie ahead. The Ice Age wasn't just a period of survival, it was a time of remarkable innovation, adaptation, and growth that shaped every aspect of what it means to be human. Understanding this period isn't just about learning history. It's about understanding ourselves and our capacity to adapt, innovate, and thrive even under the most challenging conditions imaginable. As we face our own period of rapid environmental change, the lessons of the Ice Age become more relevant than ever. They remind us that humans are capable of remarkable resilience and innovation when faced with existential challenges, but only if we can maintain the social cooperation, environmental awareness, and long-term thinking that allowed our ancestors to survive Earth's greatest climate catastrophe. The story of Ice Age survival is ultimately a story about hope. It demonstrates that even under conditions that seem impossible, life finds ways to adapt, survive, and eventually thrive. That same capacity for adaptation and innovation that carried our ancestors through the Ice Age remains with us today, waiting to be called upon as we face the challenges of our rapidly changing world. But the most chilling discovery came when scientists realized that ice ages don't just happen gradually. They can begin with shocking, terrifying speed. Deep within the Greenland ice sheet, researchers have found evidence of temperature drops so rapid and severe that they would make our worst climate predictions seem tame by comparison. We're talking about average temperatures plummeting by 10 degrees Celsius in less than a single decade. Imagine your hometown suddenly experiencing the climate of northern Alaska, permanently, within the span of a few winters. This isn't theoretical speculation. It's written in the ice itself, layer by microscopic layer, preserving the exact atmospheric conditions from thousands of years ago. When scientists extract these ice cores, they're literally holding frozen time in their hands, complete with tiny bubbles of ancient air that reveal the precise moment when our planet's climate system began to collapse. The evidence shows that around 73,000 years ago, something extraordinary and terrifying began to unfold across the Northern Hemisphere. It started subtly, almost imperceptibly, with summers that felt just slightly cooler than normal. But this wasn't a temporary weather pattern or a brief cold snap. It was the beginning of a cascade of environmental changes that would transform Earth into an alien, hostile world. Picture this moment. You're standing in what would one day become Northern Europe, but instead of the temperate forests and rolling hills we know today, you're surrounded by an endless expanse of white. The trees that had grown here for thousands of years are gone, buried under ice so thick you could stack the Empire State Building on top of it 3 times over. The very ground beneath your feet has been scraped away by glaciers moving with the inexorable force of geological time. The transformation didn't happen overnight, but in geological terms, it was lightning fast. Within just a few thousand years, ice sheets that had been confined to mountain peaks and Arctic regions began expanding outward like frozen tsunamis, consuming everything in their path. These weren't just larger versions of modern glaciers. They were continent-sized rivers of ice, some over 3 kilometers thick, carrying enough frozen water to lower global sea levels by more than 100 meters. Recent breakthroughs in climate modeling have revealed exactly how this catastrophic process began. It started with what scientists call the Arctic Gateway hypothesis. As orbital cycles reduced summer solar radiation in the Northern Hemisphere, the Arctic Ocean began freezing more extensively than it had in thousands of years. This might seem like a minor change, but it triggered a chain reaction that would reshape the entire planet. The expanding Arctic sea ice disrupted one of Earth's most crucial climate systems, the Atlantic meridional overturning circulation. Think of this as a massive conveyor belt of warm and cold water that regulates temperature across the entire North Atlantic region. Warm tropical water flows northward along the surface, while cold polar water sinks and flows southward along the ocean floor. This circulation pattern is what keeps Northern Europe habitable and prevents the Arctic from becoming completely frozen. But as Arctic sea ice expanded, it began interfering with this delicate system. The cold, fresh meltwater from the ice disrupted the density differences that drive the circulation, causing it to slow down and eventually weaken dramatically. Without warm tropical water flowing northward, temperatures across northern Europe and eastern North America began to plummet. The cooling wasn't gradual or gentle. Ice core records reveal that in some locations, winter temperatures dropped by 15 degrees Celsius in less than 50 years. Forests that had existed for millennia were killed by sudden frosts. Rivers that had never frozen solid became locked in ice for months at a time. The growing season shortened dramatically, making it impossible for many plants to complete their life cycles. As vegetation died back, it created what climatologists call a positive feedback loop. Living plants normally absorb carbon dioxide from the atmosphere during photosynthesis, helping to regulate Earth's temperature through the greenhouse effect. But as forests died and grasslands turned to barren tundra, less CO2 was being removed from the atmosphere, while more was being absorbed by the increasingly cold oceans. This might sound like it would warm the planet, but the opposite occurred. Cold ocean water can dissolve much more carbon dioxide than warm water. As temperatures dropped, the oceans began acting like massive carbon sponges, pulling greenhouse gases out of the atmosphere and locking them away in deep water. CO2 levels plummeted from around 280 parts per million to just 190 parts per million, reducing the greenhouse effect and causing even more dramatic cooling. But the most terrifying aspect of this process was the ice albedo feedback mechanism. Fresh snow and ice reflect up to 90% of incoming solar radiation back into space, while dark soil and vegetation absorb most of it. As snow cover expanded and persisted longer into spring and summer, more and more of the sun's energy was being reflected away from Earth instead of warming the surface. This created a runaway cooling effect that fed on itself. More ice meant more reflected sunlight, which meant lower temperatures, which meant even more ice. Once this process began, it became virtually unstoppable. Areas that had experienced only seasonal snow cover found themselves locked under permanent ice sheets that grew thicker and more extensive with each passing year. The psychological impact on any humans witnessing this transformation would have been devastating. Imagine watching the world you knew gradually disappear beneath an advancing wall of ice. Hunting grounds that had supported your ancestors for generations became uninhabitable wastelands. Water sources froze solid. The animals your people depended on either died or migrated to regions so distant they might as well have vanished entirely. Archaeological evidence from this period reveals the desperate adaptations early humans were forced to make. Tool technologies became increasingly sophisticated as people struggled to hunt smaller, faster prey in the harsh new environment. Clothing had to be completely redesigned to provide protection against temperatures that could kill an unprotected person in minutes. Social structures evolved to support larger group sizes necessary for survival, while maintaining the flexibility to migrate vast distances in search of resources. The Neanderthal populations of Europe faced perhaps the greatest challenge. They had been perfectly adapted to the relatively mild interglacial conditions that had prevailed for thousands of years. Their robust physiques, while excellent for cold tolerance, required enormous amounts of calories to maintain. As large game became scarce and plant foods virtually disappeared, many Neanderthal groups found themselves caught in an impossible situation. DNA evidence suggests that Neanderthal populations went through severe bottlenecks during the early stages of glacial advance. Groups that had numbered in the hundreds were reduced to dozens of individuals, barely maintaining enough genetic diversity to survive. Their sophisticated tool technologies, including the advanced Mousterian stone tool industry, weren't enough to overcome the combined challenges of climate change, resource scarcity, and competition with the increasingly numerous modern human populations. Modern humans, meanwhile, were developing the innovations that would carry them through the Ice Age and eventually allow them to dominate every environment on Earth. The pressure of survival in deteriorating conditions accelerated technological and cultural development at an unprecedented rate. Complex composite tools, sophisticated hunting strategies, and advanced clothing technologies all emerged during this period of maximum environmental stress. But perhaps most importantly, Modern humans were developing the cognitive and social innovations that would prove crucial for long-term survival. The ability to plan for future contingencies, to maintain social networks across vast distances, and to rapidly adapt cultural practices to changing conditions all became essential skills during the transition into glacial conditions. The evidence for this cognitive evolution comes from the archaeological record itself. Sites from this period show increasing evidence of symbolic behavior, including personal ornaments, artistic expression, and complex burial practices. These weren't luxury activities pursued during times of abundance. They were essential technologies for maintaining group identity and social cohesion under conditions of extreme stress and uncertainty. The creation of symbolic systems allowed groups to encode and transmit complex information about environmental conditions, resource locations, and successful survival strategies. Cave paintings weren't just art. They were libraries containing crucial knowledge about animal behavior, seasonal patterns, and navigation techniques. Personal ornaments served as identifiers that allowed individuals from different groups to recognize allies and trading partners across vast distances. This period also saw the development of increasingly sophisticated astronomical knowledge. Groups that could accurately predict seasonal changes, weather patterns, and the timing of animal migrations had significant survival advantages over those that couldn't. The ability to create and maintain accurate calendars became a matter of life and death when planning for resource storage, group movements, and reproductive cycles. The megafauna that had dominated Ice Age ecosystems were also struggling to adapt to the rapidly changing conditions. Many of these species had evolved during earlier glacial periods and should have been well adapted to cold conditions. But this particular transition was different in ways that even the most successful Ice Age species couldn't overcome. The mammoth steppe ecosystem that supported vast herds of large mammals was incredibly productive, but also inherently unstable. It depended on very specific climate conditions that created the right balance of temperature, precipitation, and seasonal variation to support the unique grassland communities that these animals required. As conditions continued to deteriorate, the delicate ecological balance that maintained this ecosystem began to collapse. Woolly mammoths, despite being perfectly adapted to cold conditions, began experiencing population declines as their preferred habitat shrank and became fragmented. These weren't just random environmental changes. The advancing ice sheets were literally bulldozing the landscape, destroying the grasslands that supported mammoth herds and replacing them with barren ice or unsuitable tundra vegetation. Giant ground sloths in South America faced similar challenges as changing precipitation patterns altered the forest ecosystems they depended on. Cave bears in Europe found their hibernation sites disrupted as caves flooded or became inaccessible due to changing topography. The Irish elk, with their massive antlers adapted for display in open woodlands, struggled as forests were replaced by dense scrubland that made their impressive headgear a liability rather than an asset. But the most dramatic evidence of environmental transformation comes from the geological record itself. Across northern Europe and North America, you can still see the scars left by advancing ice sheets with startling clarity. The landscape bears witness to one of the most powerful geological forces our planet has ever unleashed. The Scandinavian ice sheet, at its maximum extent, covered virtually all of Norway, Sweden, Finland, and much of northern Russia. This single ice mass contained enough frozen water to lower global sea levels by over 20 meters. But its effects extended far beyond simply locking up water. The sheer weight of the ice, estimated at over 10 billion tons per square kilometre, actually deformed the Earth's crust beneath it. The land surface was pressed downward by hundreds of meters, creating a bowl-shaped depression that affected drainage patterns across northern Europe. Rivers that had flowed northward to the Arctic Ocean were diverted southward and westward, creating new valleys and lake systems that still define the geography of the region today. As the ice advanced, it acted like a colossal earth-moving machine, scraping up everything in its path and transporting it hundreds of kilometers before depositing it in massive piles called terminal moraines. The distinctive landscape of northern Germany and Poland, characterized by rolling hills and scattered lakes, was created entirely by this glacial action. In North America, the Laurentide ice sheet had even more dramatic effects. This massive ice mass, centered over what is now Hudson Bay, extended from the Atlantic to the Pacific and from the Arctic Ocean south to the latitude of modern-day New York City. At its thickest point, the ice was over 4 kilometers deep, containing more frozen water than exists in all the world's oceans today. The Great Lakes were carved out by the advancing ice, which gouged depressions so deep that their bottoms lie below sea level. When the ice finally retreated, these depressions filled with meltwater to create the largest system of freshwater lakes on Earth. Lake Superior alone contains enough water to cover the entire continental United States, with nearly a foot of water. But the ice sheets didn't just carve and scrape. They created their own weather systems that extended their influence far beyond their physical boundaries. The massive dome of ice over North America deflected the jet streams southward, bringing Arctic conditions to regions that are subtropical today. The southeastern United States experienced temperatures similar to modern-day Alaska, while areas that are now deserts received enough precipitation to support forests and grasslands. These climate effects created what paleoclimatologists call the periglacial zone, a band of extremely harsh conditions that extended hundreds of kilometers beyond the actual ice margin. In these regions, the ground was permanently frozen to depths of several hundred meters, with only a thin surface layer that thawed during brief summer months. The periglacial environment was characterized by extreme temperature fluctuations, powerful winds, and ground instability that made permanent settlement nearly impossible. Yet archaeological evidence shows that some human groups not only survived in these conditions, but developed sophisticated strategies for thriving in what may have been the most challenging environments humans have ever inhabited. Sites like Dolní Věstonice in the Czech Republic reveal evidence of complex winter settlements that were occupied continuously for hundreds of years during the height of glacial conditions. These weren't temporary camps, but permanent villages with sophisticated architecture designed to withstand temperatures that regularly dropped below -40 degrees Celsius. The inhabitants had developed advanced techniques for food storage, clothing manufacture, and tool production that allowed them to maintain relatively large populations even during the harshest winter conditions. They created some of the earliest known ceramic artifacts, not for pottery, but for creating fired clay figurines that may have served important social and spiritual functions. But perhaps most remarkably, they maintained long-distance trade relationships that connected them with groups hundreds of kilometers away. High-quality flint from distant sources, marine shells from coastal regions, and amber from Baltic deposits all found their way to these inland sites, suggesting that complex social networks continued to function even under the most challenging environmental conditions. The development of these trade networks wasn't just about acquiring luxury goods. It was a crucial survival strategy that ensured access to essential resources and maintained the genetic diversity necessary for long-term population survival. Groups that became completely isolated were much more vulnerable to local disasters, resource failures, and the genetic problems that arise from inbreeding in small populations. The maintenance of these connections required sophisticated navigation techniques and environmental knowledge that allowed people to travel safely across vast distances in conditions that would challenge modern explorers. They had to understand weather patterns, terrain features, and seasonal changes well enough to plan journeys that might take weeks or months to complete. This knowledge was encoded in increasingly sophisticated symbolic systems that allowed complex information to be preserved and transmitted across generations. The famous Venus figurines found at sites across Europe may have served as portable information storage devices, containing coded information about territories, resources, and social relationships that could be interpreted by people who shared the cultural knowledge necessary to decode them. The astronomical knowledge evident in some Ice Age artifacts suggests that these populations had developed remarkably sophisticated understanding of celestial cycles and their relationship to earthly phenomena. Sites like Kostenki in Russia contain artifacts with markings that appear to track lunar cycles, seasonal changes, and possibly even longer astronomical periods. This wasn't abstract intellectual curiosity. In a world where survival depended on accurate timing of migrations, resource gathering, and food storage activities, having precise knowledge of seasonal cycles was literally a matter of life and death. Groups that could predict weather changes, animal migrations, and plant phenology had significant advantages over those that couldn't. The development of this knowledge required generations of careful observation and record-keeping, suggesting that Ice Age populations had developed educational systems sophisticated enough to preserve and transmit complex technical information across long periods of time. This represents a crucial step in the development of human culture and may have laid the foundation for the more complex knowledge systems that would characterize later civilizations. But the most profound effect of the Ice Age transition was on human consciousness itself. Living through such dramatic environmental change required psychological adaptations that may have fundamentally altered the way humans think about time, causation, and their relationship to the natural world. The experience of watching familiar landscapes transform beyond recognition, of seeing species disappear and new ones appear, of witnessing climate changes that occurred within individual lifetimes, would have created a very different worldview than that of people living in stable environments. Ice Age humans would have understood viscerally that change is the fundamental nature of existence, and that survival depends on the ability to adapt rapidly to new conditions. This understanding may have contributed to the development of the cognitive flexibility and innovative capacity that characterizes modern human behavior. The ability to rapidly develop new solutions to novel problems, to think abstractly about future possibilities, and to create complex mental models of cause and effect relationships all became essential skills during the Ice Age transition. The spiritual and philosophical implications of living through such dramatic change were equally profound. Ice Age art often depicts transformational themes, with animals and humans shown in states of change or metamorphosis. The famous therianthropes, or human-animal hybrid figures, found in caves like Chauvet and Lascaux, may represent attempts to understand and cope with a world in constant flux. These artistic traditions weren't just decorative or recreational, they served important psychological functions, helping individuals and communities process the trauma of environmental catastrophe and maintain hope for survival and eventual recovery. The act of creating permanent images in deep caves may have been a way of asserting human agency and continuity in the face of overwhelming natural forces. The burial practices that developed during this period also reflect sophisticated thinking about death, continuity, and the relationship between individuals and their communities. Elaborate grave goods, careful body positioning, and the use of ochre and other symbolic materials suggest that Ice Age humans had developed complex beliefs about personal identity and its persistence beyond individual death. These beliefs weren't just comforting abstractions, they served practical functions in maintaining group cohesion and encouraging the kind of self-sacrifice necessary for group survival. Individuals who believed their actions would be remembered and honored by future generations were more likely to take risks for the benefit of the group, even at personal cost. The genetic legacy of Ice Age survival can still be detected in modern human populations. DNA studies reveal clear signatures of the population bottlenecks that occurred during glacial periods, as well as evidence of the rapid expansion that followed as conditions improved. Many of the genetic variants that helped our ancestors survive Ice Age conditions remain common in modern populations, suggesting they continue to provide survival advantages even in contemporary environments. But perhaps the most important legacy of the Ice Age is the demonstration of human adaptability and resilience in the face of seemingly impossible challenges. The populations that survived the transition into glacial conditions didn't just endure, they innovated, created, and laid the foundation for all subsequent human achievement. The cognitive abilities, social structures, and technological innovations that emerged during this period of maximum environmental stress became the basis for the agricultural revolution, the development of complex societies, and ultimately, the global civilization we inhabit today. In a very real sense, we are all products of Ice Age survival, carrying within our genes and cultures the accumulated wisdom of thousands of generations who learned to thrive under the most challenging conditions our species has ever faced. The story of Ice Age survival is ultimately a story about hope and human potential. It demonstrates that even under conditions that seem to make survival impossible, human ingenuity and cooperation can overcome seemingly insurmountable obstacles. The same qualities that allowed our adaptability, innovation ancestors to survive the Ice Age, social cooperation, and long-term thinking, remain our greatest assets as we face the environmental challenges of our rapidly changing modern world. Understanding how the Ice Age began and how our ancestors survived it isn't just a matter of historical curiosity. It provides crucial insights into the mechanisms of climate change, the relationship between environmental stress and human innovation, and the importance of maintaining the social and cultural systems that allow human societies to adapt to changing conditions. As we face our own period of rapid environmental change, the lessons of Ice Age survival become more relevant than ever. They remind us that dramatic climate change is possible, that its effects can cascade through natural and human systems in unpredictable ways, and that survival depends on our ability to adapt quickly while maintaining the social cooperation necessary for coordinated action. The Ice Age also demonstrates the incredible power of feedback mechanisms in Earth's climate system. Small changes in solar radiation, ocean circulation, or atmospheric composition can trigger cascading effects that transform the entire planet. This understanding is crucial as we navigate our current trajectory toward higher greenhouse gas concentrations and potentially unprecedented climate conditions. But perhaps most importantly, the Ice Age reminds us that change, even catastrophic change, is survivable if we maintain the qualities that allowed our ancestors to endure and ultimately thrive during Earth's greatest climate crisis. The capacity for innovation, adaptation, and cooperation that carried humans through the Ice Age remains with us today, waiting to be called upon as we face the challenges of our rapidly changing world. The evidence preserved in ice, stone, and bone tells us that this story isn't just about the distant past. It's about understanding the forces that continue to shape our planet and our species. The same climate systems that drove Ice Age cycles remain active today, modified by human activities, but still capable of dramatic and rapid change. Recent studies suggest that current greenhouse gas emissions may prevent the next natural Ice Age from occurring for hundreds of thousands of years. But they also warn that disrupting these natural cycles could trigger other types of climate instability that we don't yet fully understand. The Ice Age experience reminds us that Earth's climate system is far more dynamic and unpredictable than most people realize. The transition into the last glacial maximum represents one of the most dramatic examples of rapid environmental change in recent geological history. But it's not unique. Throughout Earth's history, similar transitions have occurred repeatedly, each one reshaping the planet and driving the evolution of life in new directions. Understanding these natural cycles of change helps put current environmental challenges in perspective, while also highlighting the unprecedented nature of human-caused climate change. We are conducting an experiment with our planet's climate system that has no precedent in the geological record, and the outcome remains highly uncertain. The Ice Age experience suggests that the key to survival lies not in preventing change, which may be impossible, but in maintaining the adaptability and resilience necessary to thrive under changing conditions. This requires preserving the genetic, cultural, and technological diversity that provides options when circumstances shift unexpectedly. It also requires maintaining the social institutions and cooperative relationships that allow human societies to coordinate responses to large-scale challenges. The Ice Age survivors succeeded not just because they were individually resourceful, but because they maintained the social bonds and information-sharing networks that allowed groups to support each other through crisis periods. As we continue to uncover the details of how the Ice Age began and how our ancestors survived it, we gain not just knowledge about the past, but wisdom for navigating an uncertain future. The story written in ice and stone reminds us that humans are capable of remarkable achievements when faced with existential challenges, but only if we maintain the qualities that have always defined our species at its best. The day the Ice Age began wasn't just a moment of crisis. It was the beginning of a journey that would test every aspect of human adaptability and ultimately demonstrate the incredible potential of our species to survive, adapt, and thrive even under the most challenging conditions imaginable. That journey continues today as we face new challenges that will require all the wisdom, courage, and cooperation we can muster. The Ice Age taught our ancestors that survival depends not on controlling change, but on learning to dance with it. As we face our own period of unprecedented change, that lesson becomes more vital than ever. The capacity for adaptation and resilience that carried humans through the Ice Age remains our greatest hope for navigating whatever challenges lie ahead. The final pieces of evidence that confirm how rapidly Ice Ages can begin come from some of the most remote and pristine locations on our planet. In the heart of Antarctica, scientists have drilled ice cores that extend back nearly 800,000 years, creating the most detailed climate record ever assembled. These frozen archives don't just tell us what happened, they tell us how fast it happened. What they've discovered is absolutely terrifying. The transition from stable interglacial conditions to full Ice Age mode didn't take centuries or millennia. In some cases, it happened within a single human generation. Ice core data from Greenland shows that during certain transition periods, average annual temperatures dropped by 12 degrees Celsius in less than 20 years. That's not climate change, that's climate collapse. Imagine being alive during one of these transitions. You're 20 years old when the cooling begins, living in what we would recognize as a temperate European climate with deciduous forests, flowing rivers, and abundant wildlife. By the time you're 40, your children are growing up in a subarctic wasteland where trees can't survive. Most animals have either died or migrated, and winter lasts 9 months out of every year. The psychological trauma of witnessing such dramatic change would have been overwhelming. Entire ways of life that had sustained human communities for thousands of years became impossible almost overnight. Sacred sites disappeared under advancing ice. Ancestral hunting grounds transformed into barren tundra. Rivers that had provided water and fish for countless generations froze solid and stayed frozen year-round. But humans didn't just survive these catastrophic transitions, they found ways to thrive. Archaeological evidence from sites across Europe and Asia reveals that some of the most sophisticated Ice Age technologies emerged during these periods of maximum environmental stress. The pressure of survival accelerated innovation at an unprecedented rate, forcing rapid cultural evolution that might otherwise have taken thousands of years. The solitarian culture of southwestern Europe, which flourished during the most severe phase of the last glacial maximum around 20,000 years ago, developed stone tool technologies that remained unsurpassed until the invention of metalworking. Their laurel leaf points were knapped so precisely that they're less than 5 millimeters thick and perfectly symmetrical along their entire length. Modern experimental archaeologists using steel tools and decades of training struggle to replicate their craftsmanship. These weren't just beautiful artifacts, they were precision hunting instruments capable of penetrating the thick hide of Ice Age megafauna with lethal efficiency. The level of skill required to create such tools suggests that Solutrean society had developed sophisticated apprenticeship systems and technical education that could preserve and transmit complex knowledge across generations, even under the most challenging survival conditions. Meanwhile, in Eastern Europe, the Gravettian culture was developing equally impressive innovations in a completely different direction. Instead of perfecting stone tools, they became masters of bone and ivory working, creating complex composite tools that combined multiple materials for maximum effectiveness. Their bone needles were so fine that they could be used to sew intricate garments with waterproof seams, essential for survival in periglacial conditions. The social organization required to support these technical innovations was equally sophisticated. Sites like Předmostí in the Czech Republic reveal evidence of coordinated mammoth hunting on an industrial scale, with over 1,000 individual animals killed and processed at a single location. This wasn't opportunistic hunting. It was organized resource procurement that required dozens of people working together with perfect coordination and timing. The logistics of such operations were staggering. A single adult mammoth could provide food for a large group for months, but only if the meat could be preserved and stored effectively. These communities had developed sophisticated techniques for butchering, smoking, and freezing meat that allowed them to maintain nutrition through the long winter months when hunting was impossible. But perhaps the most remarkable aspect of Ice Age survival was the development of long-distance communication and trade networks that connected communities across vast distances. Obsidian from volcanic sources in Hungary has been found at sites in Germany, hundreds of kilometers away. Baltic amber appears in archaeological contexts deep in Central Europe. Marine shells from Mediterranean and Atlantic coasts travelled inland along trade routes that spanned entire continents. These weren't luxury goods traded during times of abundance. They were essential components of survival strategies that required constant contact between widely scattered groups. High-quality stone for tool-making, specialized raw materials for particular technologies, and genetic diversity for population health all had to be maintained through these networks, even under the harshest conditions. The navigation knowledge required to maintain these connections was extraordinary. Ice Age travelers had to cross landscapes that were constantly changing as glaciers advanced and retreated. Rivers changed course, and familiar landmarks disappeared under ice or were carved away by glacial action. They developed sophisticated techniques for navigation using astronomical observations, terrain features, and probably oral maps passed down through generations. Recent discoveries in cave art provide glimpses into the cognitive sophistication of these Ice Age navigators. Sites like Lascaux and Chauvet contain what appear to be star maps and seasonal calendars that would have been essential for timing long-distance journeys and predicting weather patterns. These weren't primitive scratches on cave walls. They were sophisticated information storage systems that encoded complex astronomical and meteorological knowledge. The spiritual dimensions of Ice Age survival were equally important for maintaining psychological resilience and group cohesion. Living through such dramatic environmental change required belief systems that could provide meaning and hope, even under seemingly hopeless circumstances. The elaborate cave art complexes that emerged during this period weren't just artistic expression. They were sacred spaces where communities could connect with spiritual forces and maintain their cultural identity despite external chaos. The famous hand stencils found in caves across Europe may represent one of humanity's earliest attempts to assert individual identity and continuity in the face of overwhelming natural forces. By pressing their hands against cave walls and blowing pigment around them, Ice Age humans were literally leaving their mark, declaring their presence and humanity in a world that seemed determined to erase all traces of life. But the Ice Age also reveals the incredible power of environmental change to drive evolution itself. The populations that survived glacial conditions weren't just behaviorally different from their ancestors, they were genetically different. Natural selection operated with unusual intensity during these periods, rapidly spreading beneficial mutations while eliminating individuals who lacked crucial adaptations. Modern genetic studies have identified specific variants that became common in European populations during Ice Age periods. Some of these affect metabolism, allowing more efficient processing of high-fat diets that were essential for survival in Arctic conditions. Others influence cold tolerance, improving circulation in extremities and reducing susceptibility to frostbite. Still others affect cognitive function, possibly enhancing the rapid decision-making and spatial navigation abilities that were crucial for Ice Age survival. The speed of these genetic changes is remarkable by evolutionary standards. Traits that would normally take tens of thousands of years to spread through a population became common in just a few thousand years, demonstrating the incredible selective pressure created by Ice Age conditions. In a very real sense, modern humans are genetically shaped by Ice Age survival, carrying within our DNA the accumulated adaptations of thousands of generations who face the ultimate test of environmental resilience. The megafauna extinctions that occurred during the transition out of the last glacial maximum provide a sobering reminder of just how fragile even the most successful adaptations can be when environmental change occurs too rapidly. Many of the extinct species had survived multiple previous glacial cycles, suggesting they were well adapted to Ice Age conditions. What made this transition different was the combination of climate change and increasing human pressure, creating a perfect storm that even the most resilient species couldn't survive. The woolly rhinoceros had thrived in the mammoth steppe ecosystem for hundreds of thousands of years, perfectly adapted to cold, dry grasslands with its thick fur and efficient digestive system. But as forests began replacing grasslands during the early Holocene, these specialized grazers found themselves unable to adapt quickly enough to the changing vegetation. Their extinction around 10,000 years ago marked the end of an evolutionary lineage that had successfully navigated multiple ice ages. Giant ground sloths in South America faced similar challenges as changing precipitation patterns altered the forest ecosystems they depended on. These massive creatures, some weighing over a ton, had been the dominant herbivores in South American ecosystems for millions of years. But they couldn't compete with smaller, more agile species as their preferred habitats fragmented and disappeared. The cave bear, despite its fearsome reputation, was actually a largely vegetarian species that had adapted to European forest environments over hundreds of thousands of years. As forests retreated during glacial advances and then changed composition during interglacial periods, these specialized omnivores found their ecological niche disappearing. Their extinction around 24,000 years ago eliminated one of Europe's most successful large mammals. Perhaps most tragically, the Irish elk, with its magnificent antlers spanning over 3 meters, went extinct not because it couldn't survive cold conditions, but because it couldn't adapt to the rapid environmental changes that characterized the end of the Ice Age. These impressive animals had thrived in the open woodlands and grasslands of glacial Europe, but the dense forests that returned during the Holocene made their elaborate antlers a liability rather than an asset. Each of these extinctions represents not just the loss of individual species, but the collapse of entire ecological networks that had evolved over millions of steppe ecosystem that of years. The MAM supported dozens of large mammal species across northern continents simply disappeared, replaced by forest and tundra environments that could support only a fraction of the previous biomass. For early humans, these extinctions represented both opportunity and crisis. The disappearance of large predators reduced one source of mortality, but the loss of large herbivores eliminated reliable sources of protein and raw materials that had sustained Ice Age communities for thousands of years. This resource crisis may have been one of the key factors that drove the development of agriculture and the transition to more sedentary lifestyles. The archaeological record from the end of the last glacial maximum shows clear evidence of increasing dietary breadth as traditional large game became scarce. Sites that had previously yielded mainly mammoth and bison bones begin showing evidence of intensive fishing, bird hunting, and plant processing. Communities were forced to develop more diverse and flexible subsistence strategies just to maintain adequate nutrition. This dietary transition wasn't just about finding alternative food sources, it required developing entirely new technologies for processing smaller prey and plant foods. The microliths, tiny stone blades that could be hafted together to create composite tools, emerged during this period as a response to the need for more precise and efficient processing of diverse food resources. The social implications of these changes were equally profound. Hunting large game had required relatively small groups of specialists who could coordinate complex operations. Exploiting diverse smaller resources required larger groups with more varied skill sets and more complex social organization. This may have been one of the driving forces behind the development of the larger, more sedentary communities that would eventually lead to agricultural societies. But the end of the Ice Age also created new opportunities for human expansion and cultural development. As ice sheets retreated and sea levels rose, vast new territories became available for colonization. The reforestation of previously glaciated regions created diverse new habitats that could support much larger human populations than the harsh periglacial environments of glacial periods. The Mesolithic period, which followed the end of the last glacial maximum, was characterized by remarkable cultural diversity as human populations adapted to the wide variety of new environments created by deglaciation. Coastal communities developed sophisticated marine technologies for exploiting the rich resources of newly formed estuaries and coastal wetlands. Forest peoples perfected techniques for managing woodland resources through controlled burning and selective harvesting. River valley communities learned to take advantage of seasonal flooding cycles and migrating fish runs. Each of these adaptations required detailed environmental knowledge and specialized technologies that had to be developed through generations of trial and error. The rapid pace of environmental change during deglaciation created strong selective pressures for cultural innovation and flexibility. The development of more complex social institutions during this period may also have been driven by the need to manage increasingly diverse and abundant resources. As populations grew and territories became more densely occupied, groups needed more sophisticated mechanisms for resolving conflicts, coordinating resource use, and maintaining social cohesion across larger and more diverse communities. The monumental architecture that began appearing toward the end of the Pleistocene, including sites like Göbekli Tepe, may represent early attempts to create permanent focal points for these larger, more complex social networks. These weren't just religious sites, they were social technologies for maintaining group identity and cooperation across populations that were too large and dispersed to maintain cohesion through direct personal relationships alone. The astronomical alignments and mathematical relationships evident in these structures also suggest that the detailed environmental knowledge developed during Ice Age survival was being systematized and institutionalized in ways that would lay the foundation for more complex scientific and technological traditions. The careful observation skills that had been essential for predicting weather patterns and animal behavior were being applied to understanding celestial cycles and their relationship to earthly phenomena. The agricultural revolution that followed shortly after the end of the last glacial maximum can be seen as the culmination of this long process of environmental adaptation and cultural innovation. The plant and animal management techniques that would become the foundation of agriculture had their roots in the intensive resource exploitation strategies developed during the challenging conditions of deglaciation. But agriculture also represented a fundamental shift in the human relationship with the natural world. Instead of adapting to natural environmental cycles, humans began actively modifying environments to suit their needs. This represented both an unprecedented expansion of human power and the beginning of our current trajectory toward global environmental modification. The success of agricultural societies allowed human populations to grow far beyond what had been possible during Ice Age conditions, but it also created new vulnerabilities and dependencies that made human societies more susceptible to environmental disruption. The collapse of early agricultural civilizations due to climate change, such as the end of the Indus Valley Civilization or the fall of the Maya, demonstrates that technological sophistication doesn't automatically guarantee resilience in the face of environmental change. Understanding the Ice Age experience becomes particularly relevant as we face our own period of rapid environmental change. The mechanisms that drove past climate transitions, including feedback loops, tipping points, and cascading effects, remain active in our current climate system. While the specific drivers may be different, the potential for rapid and dramatic change remains very real. Recent climate research has identified several potential tipping points in the current climate system that could trigger rapid transitions similar to those that occurred during Ice Age cycles. The collapse of major ice sheets, the shutdown of ocean circulation patterns, or the release of methane from Arctic permafrost could all potentially trigger cascading changes that would transform global climate within decades rather than centuries. The Ice Age experience also provides crucial insights into the relationship between environmental change and social resilience. The populations that survived Ice Age conditions were those that maintained flexibility, diversity, and strong social networks. They developed technologies and social institutions that could adapt quickly to changing conditions while preserving essential knowledge and relationships. Modern human societies, despite their technological sophistication, may actually be more vulnerable to rapid environmental change than Ice Age populations were. Our complex, interconnected systems depend on stable conditions and predictable resource flows in ways that could make them fragile when faced with the kind of rapid changes that characterized Ice Age transitions. The specialization that characterizes modern society, while providing many advantages under stable conditions, could become a liability during periods of rapid change when flexibility and adaptability are more important than efficiency and optimization. The loss of traditional ecological knowledge and subsistence skills that allowed past populations to survive environmental crises represents a potential vulnerability that could prove crucial if current environmental trends continue. But the Ice Age experience also demonstrates the incredible capacity of human societies to innovate and adapt when faced with existential challenges. The technological and social innovations that emerged during Ice Age conditions laid the foundation for all subsequent human achievement. The same capacity for innovation and cooperation that allowed our ancestors to survive the most challenging environmental conditions in human history remains available to us today. The key lesson from Ice Age survival may be that resilience depends not on preventing change, which may be impossible, but on maintaining the flexibility and social cooperation necessary to adapt successfully when change occurs. This requires preserving the diversity of knowledge, skills, and social institutions that provide options when circumstances shift unexpectedly. The story of how Earth's greatest ice age began isn't just ancient history. It's a blueprint for understanding the incredible power of our planet's climate system and a stark reminder of how quickly everything we take for granted can change. The mechanisms that plunged our world into a frozen nightmare 26,000 years ago, the orbital cycles, the ocean circulation patterns, the feedback loops that amplified small changes into global catastrophes, all of these forces remain active today. Our ancestors survived the ultimate test of human adaptability, developing the innovations and social bonds that would eventually lead to civilization itself. But their story also warns us that no species, no matter how successful or adaptable, is immune to the transformative power of rapid environmental change. As we face our own climate crisis, the lessons written in ice and stone become more crucial than ever, reminding us that survival depends not on controlling change, but on learning to adapt with the wisdom, cooperation, and resilience that carried humanity through Earth's darkest frozen chapters.